Hey, hello. My name is Thais Faker, and I am a current junior at Sunny Hills High School in Fullerton, California. I used to go to Harriton High School, which will make sense when my friends introduce themselves as well.
Hi, I'm Miles. I go to Harriton High School. I am a senior. That's where I met Thaddeus before we moved to Sunny Hills.
I am also a senior at Harriton High School.
And my name's Noah Braunfeld, and I am also a senior at Harriton High School.
Together, we worked with Professor Dr. Lynne Hillenbrand at the Cahill Center for Astrophysics and Astronomy at Caltech. We also worked with two professors through Dr. Hillenbrand, Dr. Rebel and Dr. Kuhn. And our research project we're presenting that we use ZTF on is the full title is a ZTF look at the optical variability of young star objects in the North American Pelican Nebula Complex. But here we have the short title, ZTF, which is Zwicky Transient Facility, look at young stellar objects in the NAP complex, which refers to the area of the sky we looked at. So we kind of want to start with a just overall physical view of young star objects in general before we get specific to what we worked with them with. So as you see here, we have an artist depiction of a young star object information, and easy nomenclature is just baby stars. And the artist depiction kind of displays this idea of a disk and accretion happening around this young star. The young star is accreting material from the disk and growing in a sense as it takes on mass from that. It's pretty violent upbringing. Stars do not have a gentle on and on to life. And a lot of our work in this dealt with the variability in the photometry we get of these stars based on their surroundings, specifically from their disk or their accretion. So, on the right, we have a Hubble images that were taken of young star object disks. And, we can see what they really look like beyond just the artistic representation. So as you can see, there's actually been a couple of papers that published in the field previously that kind of inspired our work. Big one was Cody and Hillenbrand 2018, where you see they used Kepler data and they classify objects in these regions here with different, 8 different classes: periodic, multiperiodic, burster, quasi-periodic, symmetric. And these classes are, morphological classes based on quantitative classification metrics. And the goal is to associate these, classes, we find these patterns, they often repeat themselves in different light curves with, theoretical physical causes of variability. So we have Miles going to talk a bit.
Yep. So just for example, one of these physical sort of reasons proposed for the variability, you can see on the right, we have a very, very periodic signal on a somewhat shorter time span, but this would be pretty in line with star spots on a rotating star. So we know some of the younger stars on the weak T-Tauri stars might still have a disk, but the gas might be mostly gone. So it wouldn't be affected as much by accretion, but rather by a strong magnetic field causing star spots, much like the sunspots seen on our sun. And these spots would, every time a spot rotates into our view, it would make the star appear that it's dimming, and every time it rotates away, it would brighten again. So you get a very regular pattern. And then here, following up with the paper we mentioned earlier, Cody and Hillenbrand 2018, we have a plot that somewhat inspired us later on. We'll see it, another version of this plot. But essentially what's important about this one is that we can see Q has cutoffs for periodic, quasi-periodic, and aperiodic. And here we can see it's roughly like 0.15 and 0.8 to separate these categories. And this data for Q and for fluxosymmetry came from Kepler, which is a space-based telescope, and ours obviously came from ZTF. So that had some effects on how we defined our cutoffs later on, which we'll see. And then one further difference between the Kepler and ZTF, we can see Kepler has a very high cadence compared to ZTF because obviously it's a space telescope. It can take stuff like every 30 minutes, while ZTF's is sort of limited to 1 day. And accounting for that cadence difference within Q and M was pretty important for our outcome. And we showed that using some methods, you can account for it and get pretty good data, regardless of this big difference in cadence. And here we have our ZTF. Originally we had a large sample of just shy of 700 stars. But then we culled some of them for various reasons. Number one reason, I think, being that there simply wasn't enough observations or high quality enough observations in the period. So ultimately we cut it in about half to get around 350 or so, I think, objects, which you can see in the dark blue as opposed to the light blue.
When I was introducing myself, I forgot to mention my name. Hi, I'm Owen, and we'll be talking a bit more about Q, or the quasi-periodicity metric, and M, the flux asymmetry metric. Q is used to measure how periodic a star's light curve is, while M is used to show whether the star has bursting or dipping behavior. We calculate Q by taking the variance of the residual light curve, which is a variance of the light curve when the periodic signal is subtracted from it, and dividing it by the variance of the light curve, adjusting the two measures by photometric uncertainty. We calculate flux asymmetry by subtracting the median magnitude measurement from the mean magnitude in the top and bottom 10%, then dividing this number by the standard deviation of the light curve. We use the Q and M metrics to classify stars and explore the properties each class of stars exhibits. The big challenge in calculating Q is finding the period, which is needed to create the periodic signal and the residual curve. Because of the infrequency of data, the Lomscargo algorithm we used often returns several statistically significant periods that could fit the data. Therefore, we needed to choose between them. So I created graphics like this image shown on the slide to help determine which period is the best for each star. Here I folded light curve to the four most statistically significant periods, noted aliasing here between the third and fourth most statistically significant period, and plotted the periodogram and residual periodogram. Using the period, we were able to create the periodic signal. To do this, we concatenated three folded light curves and then boxcar smoothed this new concatenated light curve. The first and last phase folded period has a big jump and a big drop, so we define the strong periodic signal as this middle period. To get the residual curve as seen in the Q equation, you have to subtract the strong periodic signal by the boxcar smoothing from the actual data. This graphic shows an example of ZTF data on low, intermediate, and high values of the Q and M metrics. Low values of M indicate bursting behavior, signified by the bottom 10% of magnitudes having a much greater distance to the median than the top 10%, while high values of M indicate dipping behavior, which is signified by the top 10% of magnitudes having a much greater distance to the mean than the bottom 10%. On the other hand, low values of Q were more strictly periodic light curves, while high values of Q are characteristic of stochastic light curves.
So yeah, you can see here, this is our version of the plot that's been kind of developed initially by Lynne Hillenbrand in 2014, among other authors, especially threshed out in its most recent iteration by Lynne Hillenbrand 2018. You can see here in our version, we scale the points according to their variability as quantified by the new metric, which has been very popular in radio astronomy, but has recently been advocated for use in optical astronomy too. And we generally see this trend whereas objects become dippers or bursters, they become more and more variable as quantified by new, which makes sense. And we see something to point out here we want to talk about is we ended up looking through every single light curve, both folded, not folded, Q and M, and compare these to different papers in the past, how they classify their Q and M. And you can see here that some regions have the colors that don't correspond to that region. You'll see here's a dominant purple region, which will correspond to quasi-periodic. we have a pretty noticeable aperiodic dipper here. And the reason for this is when we look through these, we believe that some of these light curve visually would fall more into the classes that they've been reclassified as, even though numerically they suggest to be classified in the class they should default fall into. And we talk about this more in the paper, but one of our central theses of our paper is the argument that we need to, as a scientist, as a group of people working with Q and M, we need to tailor these the calculation of these metrics and their utilization so that even though Q values between different studies may be different, the stars that are assigned in each class, such as periodic, quasi-periodic, stochastic, they are representative of a larger population class rather than restricted just to the sample of observation. So for example, if you go back a bit, in the Cody and Hillenbrand 2018 paper, you see that the cutoffs for Q are 1.15 and 0.8, but in ours you see we chose the cutoffs of approximately 0.45 and 0.87 because we believe that by using these cutoffs and as we experimented and demonstrated in paper, using these cutoffs, we create classes of objects that are more representative of multi-periodic objects, more representative of stochastic objects as they are in Cody 2018, because our data is different, so therefore our numbers are going to be a little different as we scaled our errors and stuff like that. So that's a pretty central argument we make in our paper that Q should be tailored to each study because each study is definitely going to use different data in different areas of the sky.
All right. So for this graph on the left, we are comparing our data, our periods that we got to people who have and papers that have sampled other periods are the same period, but just in a different paper. So for the most part, we do get very similar periods, as you can see. But there are two outliers which are interesting. There's one where it's like half the period and one where it's 2 times the period, and then the rest of the variances fall in these light gray bands, which is very interesting. For the middle graph, we are plotting the variability of each star, the new metric, versus the infrared color. And as you can see, after a new value of greater than 0.02, we start seeing some excess infrared color. And then after 0.04 around new, we see at least 0.4 infrared. And as you get further out with the new, you can see that we get more dippers and stochastic periodic objects and stuff. Well, not periodic, but yeah. So, and also that this infrared isn't as accurate or significant because interstellar reddening may have occurred because this is a very far away cluster compared to some others. And then the third graph to the right, pairwise KS test showed every pair of angle distributions were statistically significant, and dippers had larger angles, which is consistent with the extinction, whereas bursters had shallower angles, which is consistent with accretion. So this plot is a way to verify that the theoretical origins of the light curve variability match with their classes. This also applies to the infrared plot, where certain classes like bursters and dippers should be more variable and have more infrared excess. So in other words, using different streams of data to validate the theoretical variability classes.
Thank you, Noah. And finally, we want to talk about some takeaways. So the Q&M metrics can be used with ground-based data. Our study was the largest study so far of young star objects using Q&M. It was also the first study, it's a ZTF little science blogs. So it was the first study to ever use ZTF data on a large scale for young star objects. As talked about in the paper, ZTF is pretty famous for, transient searches. So here's something a little different we did with ZTF, which we found with good results. And, this metrics that were traditionally tested on space-based telescopes are pretty well. We showed we only had to reclassify 11% of objects, which originally we didn't know if it was possible to use Q&M accurately on ground-based data. So ZTF turned out really well for us. Our central thesis is different studies should tailor to Q metric calculation because, I think we phrased it something like, in the paper I'm trying to remember, although different studies through tailoring of the Q metric to fit their particular data may result in the same variability classes existing in different Q ranges. For example, in Cody Hillenbrand 2018, existed from 0 to 1.15 for periodics, and ours is from 0.47, 0.45. Objects within those classes are representative of a larger population rather than the small sample restricted to this study. And although we do argue that Q values should probably be normalized between 0 and 1 for interpretability between different studies. And finally, know that star know that planets. It's very important to classify young stars because their development and their growth can have profound effects on the development of exoplanets around them. For example, if we had a bursting star that had some massive bursts, then it would probably have the effect of flash burning, developing exoplanets in the inner region of the disk, and also probably in the outer region too, depending on how massive the burst is. And those are interesting effects. So we overall are very appreciative of ZTF because ZTF provided us with the opportunity to use a lot of data for free and produce some interesting analysis and learn a lot of skills from it. So that's all for us. And once again, we're very grateful for ZTF as an organization for publicly accessible data that we as high school students were able to make some interesting contributions to science because of it.